In this lesson, we'll simulate a practical example of water pumping using a real pump performance curve. Let's consider this scenario. We want to pump liquid water from a storage tank at 25 degrees Celsius and 1 bar to a higher pressure of 5 bar using a centrifugal pump. The mass flow rate of water is set to 10,000 kilograms per hour. Our goal is to simulate this operation using Aspen HYSYS and analyze the pump's performance based on its characteristic curve. In Aspen HYSYS, we use the head-flow relationship to define a performance curve. Here's the sample data we'll use in our simulation. In this table, the pump's performance is shown at different flow rates, including head, flow rate, and efficiency. Manufacturers usually provide similar tables or performance curves for their pumps. As you can see, as the flow rate increases, the head generally decreases. Meanwhile, the efficiency first increases, reaches a peak, and then begins to drop. There's an optimal operating point, and in this case, it occurs at a flow rate of around 6 cubic meters per hour. This type of situation is very common in industrial systems, HVAC, and power plants, where water must be pumped from low pressure to high pressure before entering a boiler, heat exchanger, or distribution system. First, I go to the Flowsheet Modify menu and enable the Auto Attach option so that the streams are automatically connected to the pump. Then, I drag and drop a pump onto the flowsheet. Just like before, to open the pump configuration, we can either double-click on the pump icon directly in the flowsheet, or we can click on P100 from the Unit Ops list. In the Design tab, we can see that all 3 connections, inlet, outlet, and energy stream, are already assigned. The status bar at the bottom is yellow, which means that all connections are present, but the stream data is still incomplete. Now, let's go to the Worksheet tab. Here, we see 3 streams automatically named by HYSYS: Stream 1, Stream 2, and Q100. We can rename these streams either from here or by double-clicking on each one. Let me rename Stream 2, the pump inlet, to Pump Inlet. Stream 1, the outlet, to Pump Outlet. And Q100, the energy stream, to Work. Now, we need to define the properties of the inlet stream. Let's start with Pump Inlet. Before entering temperature and pressure, let's first go to the Composition section. As in the previous lessons, I'll enter one for water mole fraction, 100%, and press Enter. A confirmation window will pop up. I'll just click OK. Now, returning to the Conditions tab, I'll enter the temperature as 25 degrees Celsius and the pressure as 1 bar. To change the pressure unit, you can use the drop-down menu, or as we learned earlier, customize it in the Unit Sets tab. Next, I'll set the mass flow rate to 10,000 kilograms per hour. At this point, the inlet stream is fully defined. Now, I'll enter the outlet pressure as 5 bar, based on our problem description. Once this is done, the status turns green and says OK, meaning that the pump is now properly configured, and all flow properties have been calculated. Let's go back to the Design tab and click on the Parameters section. Here, HYSYS has calculated the pressure increase as 400 kilopascals. The pressure ratio is 5.0, and the required duty or shaft work as approximately 1.47. On the right-hand side, we see the adiabatic efficiency set by default to 75%. We can change it, for example. If I reduce it to 60%, you'll notice that the power requirement increases to about 1.84 kilowatts. This makes sense. The lower the efficiency, the more power is needed. One more note. Instead of entering the outlet pressure directly in the Worksheet tab, you can also define either the pressure increase or the pressure ratio, and HYSYS will automatically calculate the outlet pressure. Now let me show you something important. To demonstrate this, I'll go to the Worksheet tab and remove the outlet pressure of the pump. As you can see, the status bar at the bottom turns yellow again, and the message says unknown duty. This means that the pump doesn't have enough information to calculate the pressure rise or the required power. Now let's go back to the Design tab. This time, instead of defining the outlet pressure directly, I'll enter the pressure ratio as 5 and press Enter. And as you can see, the result is exactly the same. HYSYS automatically calculates the pressure increase and the outlet pressure accordingly. I can also clear the pressure ratio and instead enter the pressure increase as 400 kilopascals. Once again, the result remains consistent. HYSYS calculates the corresponding outlet pressure and all other related values. So, remember, you can define any one of the following: outlet pressure, pressure ratio, pressure increase, and HYSYS will compute the rest automatically. This gives you flexibility in how you define the pump's performance, especially useful when exact outlet pressure isn't known, but the expected header ratio is available. Up to this point, we've been using a simple pump setup, defining only the efficiency. Now we'll replace this with a real performance curve to simulate the actual behavior of a centrifugal pump. To do this, go to the Rating tab and click on Add Curve. In this window, we can define the pump's characteristic curve by entering values for flow rate, head, and efficiency. Let's enter the data based on our problem statement. Close the curve input window. Then, make sure to check the box Use Curve, so HYSYS will use this performance data for pump calculations. However, after enabling the curve, you'll notice that the status bar at the bottom of the pump window changes from green to yellow, and the message says Overspecified. This means we've provided more information than necessary. Since the performance curve already includes head and efficiency data at various flow rates, we should remove any manually entered values that conflict with the curve. To fix this, go to the Design tab, and under the Parameters section, delete the pressure ratio, delete the adiabatic efficiency. Now, HYSYS uses only the data from the performance curve, and as you can see, the status bar turns green again. It also calculates the pressure rise, pressure ratio, and adiabatic efficiency based on the flow rate and the curve. If you now switch to the Performance tab, you'll see detailed performance data for the pump. At the current flow rate of 10,000 kilograms per hour, which is approximately 10 cubic meters per hour, HYSYS shows head is around 38 meters, power is around 1.59 kilowatts. Now let's try lowering the flow rate. I'll change the mass flow rate to 6,000 kilograms per hour, roughly 6 cubic meters per hour, and go back to the Performance tab. You'll see that the head increases to about 48 meters, and the power drops to about 1.0 kilowatts. That makes perfect sense. Lower flow means less power required, but higher head is delivered. Now let's return to the Design. Parameters tab. You'll notice that the adiabatic efficiency has updated to around 75%, which matches exactly what we defined in our performance curve for this flow rate. So HYSYS is now using our custom pump curve to accurately simulate how the pump behaves at different operating points, which is much more realistic than assuming a constant efficiency. In the next lesson, we'll move on to modeling a compressor. We'll look at how to define its input and output conditions, set efficiency parameters, and explore how it behaves under different operating conditions, just like we did with the pump.